All right, my dear friends, welcome back, and let's start lesson number 18, and we're going to be talking about linked lists again. Basically, we're going to continue on what we have covered and talked about so far about linked lists. In this presentation, I'm going to just introduce more and more operations on linked lists and how to perform them, and then develop a basic code to implement that. Okay. Part of these operations is creating a new list node, and we already did that. And then we have talked already about setting a position of a particular node in the list. And then we know now how to insert a node to a list anywhere along the list. Okay? Today we're going to talk about deleting a node from a list. So I want to go to a particular node and then delete it from the list, and of course keep the continuity of the list so that I don't lose any of the other information that I have in the rest of the nodes. And as well, in this presentation we're going to perform some sort of traversing to the list, and this time I'm not going to leave it as an exercise for you. At least graphically I'm going to show you how we're going to do that and put the main structure for that. And part of the traversal, as we talked about the other time, we're going to write a code to find the list, the size of the list in hand. And we're going to write a little piece of code to find a particular node. So we're going to be performing some sort of a search in an existing list looking for a certain target. Okay, then we're going to start from the node deletion in this lesson. And again, the question is, where from in the list that node is, and which one I need to delete. Well, again, the scenarios are basically the same. It's either going to be the very first node in the list, or it could be some node in the middle, somewhere along the list, or it could be the very last node in the list. We're dividing the scenarios this way because, as we have seen in the case of the insertion, we have to be a little bit careful when we delete a node from here or there. So slightly different the operations are, and sometimes we have to make some precautions before we do this step or that step. Okay? So after that, the question is then, okay, I know where the node is now. How am I going to delete it without losing the rest of my list? Let's try to do that first graphically, the way we did it with other functions, and then after that we're going to develop the code which describes the operation and implement the operation. Okay, we're going to start from the first scenario to where I would like to delete a node which is pointed by head, the first node in the list. Here's my list. Although I have it graphically on the screen for you, I would like to write it down in here as well to make more illustrations. Okay, so head is pointing here, all right? And here's the list connected like that with my magic pointers, all right? And I would like now to delete this node. What do? Well, first of all, I have to set a pointer that points to the node I want to delete. I want to mark it, basically. In this case, because it's the first one, it's very simple. You just make current equals to head. Okay, and that's it. However, we're going to repeat this step for the other scenarios, and that's why we're going to call it a step in the process, and it's step number 0. So first of all, I'm going to set position, okay, to point to the node that I would like to delete. What do I do after that? Well, here's current pointing to my node, and now the next step. Basically, instead of having head pointing to this node now, I would like to make it point here. So instead of being pointing to this node, I would rather make it point to this one. Okay, so this is step number 1. And now, is my list connected? Yes, for sure. I'm pointing to this points to the one after that, pointing to the next, to the next, to the next, till I reach the end of the list. I'm happy, I'm done. Well, not really. As far as actually the list goes, yes, you're done. And this node is out of your list now, and your linked list is actually safe, and head is pointing to it. What is the problem then? Well, there is a little problem with memory usage and memory leak. Well, this node in here, yes, you deleted it from the list. It's not in the sequence, but physically it still exists in the memory, and it's still taking space in the memory, the size of whatever the node is. Okay, and as I said earlier, the size of the node itself could be huge. It could contain a record for a patient which has lots of data inside it. 1K, 2K, 10K, I don't know. So by migrating and removing the head from pointing to here to somewhere down here, that means that doesn't mean that this space has been freed. Okay, so the list is okay, but the memory is not okay yet. So there is one more step that I need to do. What is that step? Yes, it's exactly to free the memory. I have to free this space and make it available for users after that. So the next step I'm going to do, my list is healthy now. It's all connected together, no problem with it. However, I have to delete this node. To delete it, I'm going to use the function free. Okay? So basically, I need to free the space allocated by this node. Never forget this. Yes, your list is healthy and everything is excellent, but in terms of memory, we're not doing the best thing if we don't do this. And as we run and exercise with our program again and again without freeing this, your memory is going to be filled with unfreed nodes, and you cannot reach them and you cannot access them, and actually you don't need them. Okay, and you cannot see that in your eye, definitely, because it's in the computer RAM, and you don't know what's reserved and what's available for other applications and other users. So never forget to go through this step. Okay, so that's deletion from the top of the list. Very simple, very straightforward. 3 steps: mark the node you need to delete, then make the pointer point to the node right after that, and then number 3, free the space allocated for the node you deleted. All right, let's see how we delete if I'm in the middle of the list, and let's see how different it is from deleting the first one. Let's say I would like to delete this node. What do I need to do? I need to set position again. All right, setting the position means I need to start from here and keep going till I find my target. Make current pointing to that node. Okay, what do I need to do after that? In the case of head, when I was deleting from the top of the list, I know what's pointing to this. All right, it's head. What points to this node now? Where's my mouse? Okay. What points this node? It's this pointer. Okay, what is this pointer? Well, I don't know. I have to go back to this node, all right, and see what that is. True? And that means I have to start all over again till I get to the node just before the node I want to delete, and that's when I know what is this pointer. Okay? Why do I need this pointer? Yes, this pointer is now pointing to this, and I want to make it point to the next one. Right? And that's why, basically, I have to go twice through the list from the very beginning to around the node I want to delete. The first time, I would like to mark this one as the one I want to delete, and I have to keep a pointer here. Why do I have to keep the pointer here? Well, because the very last step is always to delete the node, right? And to delete a node, I need a pointer, okay, so that I can say delete, free that pointer. And that means free the block this pointer is pointing to. So yes, I need a pointer which points to the candidate node, the one which I'm going to delete. And I need another pointer here so that I will use whatever pointer it's pointing to so that it goes to the next line. So step number 1 was, or step number 0 according to our convention in here, is to set the position. And then in step number 2, to where I went back from the very beginning of the list till I got to this point, to the node just before target, and then I'm not going to make it point now point to this node, but rather I'm going to make it point to the one just after it. Okay, and that means basically 2 steps. Okay, I could write this step number 1 like this. Let's call this node in here P. Okay, so let's say I'm gonna be doing something like this: P arrow next, okay, equals to current arrow next. So this means, okay, make this node P point to whatever current is pointing to, which is, if you like, this one. That's current arrow next. It's this arrow. So make this point to this one. That's one way of doing it. Another way of doing it is simply by saying something like this: make P arrow next. So it is again this pointer. I'm assuming here that this is called P. All right? Make this point to which one? To arrow next. That's this one, arrow next. So it will be something like P arrow next equals to P arrow next, and this where the I'm pointing to the next one. However, not this one, but the one after, and that means arrow next, something like this. So by saying P arrow next, that means here. Okay, that's not the one. I want the one which comes after that, next to that, this one. So this is B arrow next, this node, and arrow next from there. Okay, so I either do this or do this. They both mean the same. Okay, and what do I do after that? Of course, the list is healthy, but the memory is not. And then I have to delete this node and take it out of the memory. So the third step is to free the space. Do free current, and that way this will go out of memory. Okay, the third case is when I want to delete from the end of the list. So I want to delete this node. What do I need to do again? Well, basically, I'm going to run from the very beginning. Keep going till the node you're at, arrow next, points to null. That means this is the last one. Okay? Put your current there. True? So that's basically step number 0 in the process. And what do I do after that? Well, basically, I need to go again from the very beginning because I need to know this one. I always use this one, and there is no other meaning of knowing what is the pointer to this, what is the address of this when I'm sitting here. As I know, I can see forward, but I don't know what's happening behind me. Okay? So to know what's happening behind me, you have to start all over from the very beginning and then get to the node just behind me. And that's what we do then, and I stop here again. All right? So this is node P, pointing to current. And what do I do after that? Well, simply, instead of making this point to this node, to current, I'm just going to make it point to the node after that. Well, there are no nodes after that. Actually, this one is pointing to null. Well, simply make this point to whatever this one is pointing to. So if this points to null, all right, make this point to null now. All right? So it's the same thing. And then after that, what do I do? As usual, free the space so that we make this space available for other applications and other users. So again, whether the scenario we're talking about is at the beginning or from the middle or at the end, it's pretty much the same. You have to set positions first to go point to the node you want to delete and to the one just before it, because you're going to use the pointers from that. And then the second one, make the whatever node before the current node point to the one next to node through either this statement or this statement, because physically they mean the same. And after that, you need to free the space. The same exact three steps that we're going to perform each time we want to delete a node. So regardless where that node is, although we had three different scenarios, it seems that the delete process is going to be the same for all scenarios. All right. Comments on the node deletion process. The list has to be traversed to locate the target node to be deleted. And that's by going from the very beginning till I find target and make current. Let's say this is my target. Okay? So if that's my target, then I traverse from the very beginning. I put current first here, and then I start advancing it till I get to this node, and as a result, I will make current pointing to the target node. This is my target. Whatever I have inside is actually my target. Okay? So that's the first step in the process. Once I found my target, the list has to be traversed again to locate the node prior to target. And why do I need that? As I said, well, because I'm going to use the pointer inside it to point to the next one in row. All right? And while I'm sitting at current, there is no chance, no way for me to know what is the address in there. All right? So I need to traverse. Well, this is unfortunate, but I have to do it. I have to traverse the list again till I get to the point just before my target point. Okay? Basic assignments that I need to do after that. Well, basically, I'm going to do something like current arrow next equals to target arrow next. And in this piece of code in here, actually, we're assuming the following. We're assuming, here's my list. In the statements you see on the screen, we're assuming that the first pass that I go through the list to find the node I want to delete returns back to me a pointer called target. So target actually points to the actual node that I want to delete. However, the second pass that I go through to locate this one just before it returns to me a pointer called current. So this is different from what we were talking about in the other pieces of papers. Okay? So basically, in the first round, I will find target. In the second round, I will find current, which is just before this. And then, based on this, I'm just going to say current arrow next, point to target arrow next. All right? And that's the statement we're saying in here. Current arrow next, point to whatever target is pointing to. Or, as I said before, equivalently, I can say current arrow next equals to current arrow next. And that means the one which comes after the second or the next node in list. Okay? And what do I do after that? So this is the first assignment that I do. The second assignment, free target. Free this node after you're done with it. The list is healthy and it's all connected together. However, this node has to be freed to make the space available to other users. And that way, I'm not going to have any memory leaks. All right? Well, based on this, let's now develop the code which performs this deletion process. Well, I'm not going to write the whole code in here. I'm just going to write the portion of the code which actually talks about this process. So at this point, I'm assuming that target has been located somehow. So I traversed already the list from the very beginning and found the target node that I want to delete. What do I need to do after that? Well, the next step is then to traverse again the list to find this node which comes right before the one that I want to delete. Okay. So what I'm doing, this is the second pass to find current. Current is going to start at head from the very beginning. And then what I'm saying in here, while current arrow next, while the one which comes after current is not target node, okay, advance your pointer forward to point to the next node. So basically, if you don't find target ahead of you, then please increment and go point to the next node. So in that case, I say current equals to current arrow next, and that means go to the next node. So keep going forward a node each time, and each time you're at a certain node, look ahead of you. Is target, is the node just ahead of you? If that is the case, you're through and you're done with this loop. Otherwise, you just advance your pointer to point to the next node in the list. Okay, so I reach here outside this while loop when I find current. So by now, target is known, current is known. What do I need to do? Well, it's exactly the two assignments. By this, we did the set position thing. Step number 1 is to make this assignment, which we said current arrow next equals to current arrow next arrow next. I either can do this or just simply say current arrow next equals to target node arrow next. Okay, but as I said, it's the same. So this is the first assignment, and then after that, I can safely now free this node, which is called target node. So I'm using the function free in here. So basically, what I have in this piece of code here is the main 3 steps that I need. The first step is to locate the node just before the target node to be deleted, and then I'll make the assignment of migrating or moving this pointer to point to the next node, and then step number 3 to free this node. Very simple, very straightforward. And this works for any node in the list, whether it's the first, somewhere in the middle, or at the end. As we have seen in the graphical illustrations, we're always going to go through the same 3 major steps. Okay, now the next function we want to talk about is traverse a list. What if I want to visit every node in the list and perform certain operation on that? How do I do that? Well, simply, I'm going to start from the very beginning. As we have already noticed that anytime I would like to access the list, I'm going to access it from the very beginning. And the accessing is going to be sequential, one node after the other. I cannot randomly access that list. Okay? I cannot go to the 5th node in the list unless I go through the 1st, 2nd, 3rd, and 4th. Okay? And then I can see the 5th. All right? And then to traverse it, to perform any kind of operation on any of the nodes in the list, or let's say on all the nodes of the list, like I'm going to go, these are the records of my students, my lovely students like you, and I would like to give 5 points bonus to everybody. All right? In that case, I will go to every record, make the grade increased by 5, and then go to the next, increase the grade by 5, and so forth till I find null. In that case, I have visited all nodes in the list. So the way to do that is simply, I'm gonna start with a local variable, basically called current, and I will make current at the very beginning equals to head, pointing to the very first record in the list. Okay? And I basically, I'm gonna go through all the nodes till I encounter the null pointer. Once I find this null, then I'm through with all the nodes in the list. So basically my loop here says, while current does not equal to null, that means there are still more nodes to cover, perform the operation, whatever that operation is. Give bonus grades, give bonus salary, do whatever you would like to do. It all depends upon the operation. I'm always giving the good examples. Raise in salary, bonus in grades, something like that. You can, of course, do anything else you would like to do with each nodes. What matters is actually is that we're visiting every node one after the other sequentially from the very beginning in here till I encounter the null. So perform whatever kind of operation you would like to perform on the current node, and then advance current to point to the next. So basically, after I'm done with the operation, I will say something like current equals to current arrow next. So that's basically the skeleton, the main loop in the traverse program. Okay? So what we're going to do, we have perform the operation on the first node, and then I'm visiting the second node now, and then the third node, the fourth, and so forth. Each time I check, am I reaching null? No, it's not yet. Still, I have some flesh here. I have some nodes. Okay, work on that. Perform the operation. Advance to the next. All right. What am I having in here? Null. Okay, you're at the end of the class. You're at the end of the list. All right, we're through with all nodes. Then I stop. The while loop in here is gonna exit. Okay, so that's basically the traverse function. Very simple. Yes, I left it as an exercise for you in other implementations, of course, when we were talking about stacks and queues, but more or less we're talking about the same thing. Basically, to visit every single node in our list or in our structure and perform certain operation in there, and then move on to the next entry in your list. Okay. What do you want to talk about after that? As an example on traversing a list, we would like to develop a function that will find the size of the list. How many nodes do I have in my list? Well, sounds very simple. Why is that? Well, when we defined our list structure, we said list has two main entries in there, at least the way we wrote it. We said list is a structure that has an integer called count and a pointer to a list node called head. All right? Well, this count is going to always contain the number of nodes that I have. So each time I insert a node, I increment count. Each time I delete a node, I decrement count. Well, big deal. Then the whole function is just return a count. Well, that's not always the case, as a matter of fact, because not everybody actually implement the list the way we implemented it. Typically, what people do is simply something like this. They would have their head defined just like this. List node, and that's the variable name of the structure defining a node, pointer, head. And that's the only thing we have. And they just, after this, allocate space for this pointer. And that's what they do. They don't have count. They don't have really a structure in here to where they have the integer count and the pointer head. It's just this one. And this is sufficient, actually, to identify a list. All I need to identify a list is just a pointer that points to the very first node in here. And this is a pointer that points to a list node. So this is sufficient, actually, in this case, to identify a list. If that is the case, then I would like to know how many nodes I have in this list. Well, there is no means to know that unless I actually traverse the list. So that's where we're going to use this function. Find a list size. We call this function list length, and it basically finds the size of a list. The prototype for it, it's going to return a value of integer, and that basically counts the number of nodes. And here's the name of it, and it takes as an input the list that we have. It could be just head, but to be consistent with our illustrations, we always refer to the name of it as list. But I'm not going to look at count. We're going to do it the hard way. Okay, the precondition for this is that this list is already created, it exists, all right, and it has some nodes inside it. Maybe no nodes, that's fine, but at least has been initialized, created. All right, what do I get after I run this function? Well, simply the function returns the size of the list, okay? And it keeps the list unchanged. I'm not gonna touch it. All right, let's see how to implement that. Well, basically, here's the implementation. I'm gonna define a local variable called size, and that's gonna contain the number of nodes in the list as we move on along the road. And basically, I'm not gonna change the position of head, because if I change the position of head, traversing the nodes using head, then I'm afraid I'm gonna lose these nodes. So I'm not gonna touch the list itself, and that's why I'm defining a local variable here called current, okay? And current points to a list node, and I'm initializing it to point to head. So it's pointing the same thing as head. So this is current. And now, the same as with the previous pictures that we have seen, current is gonna now visit every node in the list till we encounter null. Each time, it's gonna perform the operation in the traverse. Well, what's the operation? Just if that thing is not null, just increment size by 1, because I have one extra node. So basically, the whole operation that I'm going to perform is just increment size, and then point to the next one. True? Very simple, very straightforward. And I return. Okay? Once I get out of this loop, I'm going to return size as my return value to this function. And this way, size will contain, or the return value of this function is going to contain the number of nodes contained in this list. Okay? It's very simple, very straightforward. So even if I don't have that count in the structure, I can always find it in this way. Another example. I want to find a target node. I want to search my list, looking for a particular node. Well, fine, we do that a lot. It's a searching process. I want to find the record for Antonio, one of the students in my class. And I have in this list all the records of all students in my class. All right? The key is the name Antonio. So I'm going to visit again all the nodes in the list. Each time I visit the list, I'm just going to check, is the name there Antonio? If yes, just return a pointer to it. Otherwise, keep going till you encounter null. In that case, Antonio is not in your class. He is somewhere else. Okay, let's see. Target checks if a node containing target is in the list. The prototype for that is just a Boolean, which is going to tell me yes, found or not found. And in case it's found, I would like to return a pointer to it. Okay, so PTR here is going to point to the record of target. All right? And so what I have here, I'm looking for target, the name Antonio, let's say, in this list. And once found, and when you say yes in here, I would like PTR, this pointer, to point to that record. All right? Let's see. The precondition, the only thing is that the list exists and it has been created and initialized. The result, as I said, Boolean value here saying yes, found, or no, not found, true, false thing, and a pointer which points to target in case of a successful return, or otherwise make this point to null. Okay, let's see. Very simple. Okay, make current my local variable. At the beginning, initialize it to point to where head is pointing. Okay, same as we did before. And again after that, my major loop, which says while current arrow next, or while current does not equal to null, I'm not through with the list. Okay, check the current node. Is target equals to the entry in there? If yes, I'm happy and I found Antonio, my target. Okay, then basically make pointer equal to current. That means make PTR pointing to the same location as current is pointing to, and return true, fruitful search. Otherwise, I'll just simply need to go to the next node. Okay, and the next node, I'm going to check again. Am I at the end of the list? Okay, if not, then again check the entry in there and see if it equals to your target and make the return and so forth. If I end up with a null and I did not return in the middle of this loop, that means I have exhausted the entire list and I could not find Antonio in my class. So in that case, I'm going to return a null pointer in here and a false, indicating that the search was not fruitful. So very simple, very straightforward. These are two examples on traversing actually a linked list. And that's very simple. Okay. That's pretty much what we would like to talk about in lists. However, the linked lists, generally, we have so many applications that use linked lists, as a matter of fact. And we can basically classify these applications into basically two categories. What's so-called general purpose lists or restricted lists. What are these general purpose lists? Actually, any application that would require some sort of allocation on demand. So it's exactly the basic idea behind using linked lists rather than static arrays. However, I could keep my records in the list ordered in a certain order, ascending or descending, or I will just keep inserting at the very end. So always insert at the very last end of the list each time. Okay, and that way I don't worry much about the ordering. Does it matter if I keep my list ordered or not? Well, let me put the question in a different way. Can I use binary search? Remember the searching algorithms? We have sequential search and binary search. Sequential search to where you have to visit every entry in the array or in the structure in general, from the beginning to the end. Okay. However, binary search works on ordered lists. And we said we're going to go to the middle and then forget about the half of the list, go to the proper half because I know my item is less, and so forth. I keep dividing by 2. Does this work in case of lists? I'm afraid not. Why is that? Well, simply because if I have this long list, to get to the middle of it, I'm going to go through all of these till I get to the middle. All right? And then I check target with whatever I have in here. Oh, target is less. Oh boy, I have to go back. Well, I can't go back, unfortunately. I have to start all over again and move forward sequentially till I get to wherever I would like to get. Okay? So the way linked lists are designed actually is to work for sequential searches only. So binary search simply cannot be used. So why bother having ordered lists? Well, it could help sometimes, especially in a non-fruitful, non-successful searches. Let's say I'm searching for Antonio in my class, for the record of Antonio again in my class. Okay? However, my class this time is ordered alphabetically, according to the name. Okay? So I visit the first one. Is it Antonio? No, it's not Antonio. Well, is the letter in there less than Antonio? If it's less than Antonio, that means, okay, there is still hope. I might find Antonio in the neighbor node. So go to the next, and so forth. Well, I reach a point, let's say after the second, the third, the fourth, okay? I find a name starting with a W. Well, W comes after T. Then there's no chance that Antonio is in the list. So I'm not gonna actually search in the rest of the nodes, so I exit. So actually, keeping the list ordered could help sometime, especially when I'm searching for someone who's not there. Okay? But other than that, it's not the same as arrays where I can use binary search rather than sequential search. Sequential search is the only technique that we use. Okay, restricted lists. Restricted lists are special purpose lists that we access them in a certain fashion. Well, how about queues and stacks? We talked about these, right? They're lists. However, we don't access any record in the middle. The accessing is somehow restricted. Either a FIFO or a LIFO, first in, first out, last in, first out, stacks and queues. So actually, although we implemented these stacks and queues using arrays, yes, dynamic structures, but yet we used the static array structure and we had to define the maximum size. Well, I could have the problem of overflow or the problem of underflow. So I could implement then stacks and queues using linked lists rather than using arrays from the very beginning. And that these kind of linked lists are called restricted linked lists rather than general purpose linked lists. So next time we meet, we're going to be talking about the implementation of queues and stacks using linked lists instead of arrays. And that's hopefully going to be more efficient, better utilization of the computer resources, especially the memory, which we all care about it. Okay, that's all I'm going to talk about today. Thank you very much for listening. And if you would like to refer to this material on the internet, you go to the UNINETTUNO website and you click on the Mid-NetU project, and you're going to find lots of interesting stuff. Thank you very much again. I'll see you later.